In the middle of the last century, few people were interested in climate change. Levels of greenhouse gases in the atmosphere were unknown. Temperatures were being recorded, but no one was assembling them to make an accurate global picture. At this time, a young researcher called Charles Keeling was working out a way to measure the level of carbon dioxide in the atmosphere. He found concrete proof that as the level went up and down with the seasons, it was also steadily rising. A few scientists had already said this was likely. Burning fossil fuels rapidly releases millions of years of stored carbon back into the atmosphere. And it was concerning. As a greenhouse gas, carbon dioxide acts like a blanket that traps the heat, so it causes the whole planet to warm up. Fast forward to the present day. We now have a complete picture of how much carbon dioxide has risen in the atmosphere. The level is still rising, and in 2021, it had increased by an astonishing 50% since humans embarked on the Industrial Revolution. But it's the rate of change which is most concerning. Over the last 120 years, other major factors that could influence global temperature have had negligible impact. Factors such as the amount of energy from the sun or the amount of dust from volcanic eruptions that would block the sun's energy from getting through. So, we know that rising levels of greenhouse gases have been the main influence on the climate over the last 120 years. But how much have they affected the temperature of the planet? Years of records from all over the world have now been brought together to give us a picture of how the overall global temperature has changed over time. As expected, it's risen. The temperature is now far higher than it was a century ago. But it's the rapid rate of warming that has been most concerning. The true effect has been masked, though, because 90% of the extra heat has been absorbed by the oceans. Since 1955, we've been able to monitor this too. Over many years, the heat will gradually be released again back into the atmosphere. Even if levels of greenhouse gases can be reduced, unfortunately, this heat will keep global temperatures higher than they otherwise would have been. So far, we've looked at the overall effects, but let's now see how temperatures have changed in various locations across the planet. Let's start in 1901 and run through the years to the present day. The pins show the difference in temperature relative to the middle of the 20th century. Blue pins are cooler. Red pins are warmer. The longer the pins, the greater the difference. Watch how the cooler blue areas gradually disappear, and then the warmer red pins take over as the planet warms up. You can see how the warming has accelerated, particularly in recent years, and some areas have warmed more than others, especially the Arctic. This Arctic warming has had major consequences. Since 1979, satellites have been able to monitor sea ice, and the amount in the Arctic has reduced dramatically. Ice is good at reflecting heat back into space, so the reduction has caused the ice-free ocean to absorb even more heat than it previously would have, causing yet more warming. If we look at the temperature records for Svalbard within the Arctic Circle, the rise has been particularly noticeable in recent years. This has led to the glaciers there dramatically reducing in volume. This shows how the glaciers were in 1936, and this is what they're like now. The red areas highlight how much ice has melted away. But it's not just at this location. In only the last 40 years, the average thickness of the world's glaciers has reduced by 24 meters, the height of an 8-story building. Ice sheets are reducing too. We've only been accurately monitoring these since the 1990s, But in that time, Greenland alone has lost nearly 5,000 gigatons of ice. When melted, that's almost double the volume of Lake Victoria in Africa. All the meltwater from land-based ice sheets and glaciers flows into the oceans, causing the sea level to rise. This is made worse by the ocean waters expanding in size as they warm. This graph shows the global rise in sea level over the last 120 years. Half the increase has happened since the early 90s. As with temperatures, some areas are affected much more than others. Some low-lying areas are already under threat. It is difficult to prove that specific weather events are caused by climate change. But we do know we have seen more extremes as the planet warms. There's been an increase in heat waves, with many temperature records being broken. Changes in rainfall patterns have led to more frequent and severe weather events at either end of the scale, from droughts to floods. The past 9 years were the warmest on record globally. When Keeling first made his discovery, we had little evidence of climate change, but as each year goes by, we gather more data showing how much the climate is changing. Can volcanoes affect our climate? Volcanic eruptions can certainly emit huge quantities of material into the atmosphere, but ash falls quickly back to Earth, and the amount of carbon dioxide emitted from even the largest historic eruption is hundreds of times less than our yearly emissions from burning fossil fuel. Volcanoes also release sulfur dioxide, and that's a different matter. If the eruption is large enough for it to reach the stratosphere, the sulfur dioxide converts into tiny particles called aerosols that remain suspended there. These reflect the sun's energy back into space, which cools the planet. This is what is registering on the graph you can see here. The peaks coincide with major eruptions, and the most significant was the Mount Pinatubo eruption in 1991. It ejected more sulfur dioxide than any eruption since Krakatoa in 1883, and it's thought to have cooled the planet by 0.5 degrees Celsius. The effect on the climate only lasted about 3 years, however, and it didn't reduce the long-term trend in a significant way. The sun is the most important energy source for life on Earth and is fundamental to its weather and climate. The amount of energy we receive from the sun varies naturally over time. So could this variation be contributing to our current rapidly rising global temperatures? Let's take a look at the science and find out. Since the 1970s, satellites have been used to provide accurate live monitoring of the sun's energy, but clever techniques using ice cores, for example, give us information about the sun's activity for thousands of years back through history. This shows us that the sun's activity cycles over time, repeating about every 11 years. At its peak, there's an increase in sunspots and solar flares, with spectacular aurora displays in polar regions. This graph shows us that while solar activity peaks and troughs, the planet has continued to warm regardless of this cycle. Extended periods of low sunspot activity can help explain extended cold periods in some regions, such as the Little Ice Age in the late 1600s. But scientists agree that recent trends in global average temperature rise are much more widespread across the globe and cannot be explained by this 11-year cycle. In fact, recent solar cycles have actually shown a lowering in activity, suggesting that rather than causing the recent warming, it would instead be a factor for cooling. We may even be heading for what scientists call a grand minimum of solar activity. But studies have shown that while this might cool the planet as much as 0.3 degrees Celsius, this would, at best, slow down but not reverse human-caused global warming. A much more dramatic effect on the global climate is caused by the cycle of the Earth's rotational axis and orbital path around the Sun, causing the climate to slowly change over thousands of years. In fact, it's sufficient to push the Earth in and out of glacial periods when ice sheets cover large portions of the planet. The last glacial period finished around 12,000 years ago, and currently the orbital cycles should be causing the Earth to cool again very slowly over thousands of years. This is the opposite of the planet's current rapid temperature rise observed over a much shorter time. So we know that neither the planet's position relative to the Sun nor the solar energy cycles are responsible for the rapid warming of the Earth we see today. The Earth's atmosphere contains 78% nitrogen and 21% oxygen. The other 1% is made up of greenhouse gases, such as water vapor, carbon dioxide, methane, and nitrous oxide. That tiny 1% is crucial for regulating our climate. Without greenhouse gases, the Earth would be far too cold to live on. They act like a blanket, keeping the planet warm. As with the glass in a greenhouse, they help to trap the heat from the sun that would otherwise radiate back into space. So why do we want to get rid of them? Because human activity is rapidly increasing the levels of greenhouse gases in the atmosphere. This is heating the planet beyond the level that many plants and animals are accustomed to, and faster than they can adapt. This shows all the main contributions humans make to our climate, representing both warming and cooling effects. The main greenhouse gases are highlighted, with carbon dioxide having the largest warming impact. Since parts of the world became industrialized, the level of carbon dioxide in the atmosphere has increased by a staggering 50%, and the increase is accelerating. By using methods such as analyzing samples from the bottom of the ocean, we now know the level hasn't been this high for at least 2 million years. It would be even higher if some of the extra carbon dioxide hadn't been absorbed by the land surface and oceans. Methane is the second highest contributor. There's around 200 times less of it in the atmosphere, but it's much more effective at trapping heat than carbon dioxide. Since pre-industrial times, its level has more than doubled. In fact, it's risen an astonishing 10% in just the last decade. By far, the most abundant greenhouse gas is actually water vapor. It's created by evaporation and removed by rain. The amount of water vapor in the atmosphere varies with atmospheric temperature. For every 1 degree Celsius of warming, the atmosphere can hold 7% more moisture. But remember that water vapor is a greenhouse gas, so that extra 7% will cause even more warming. It's a feedback loop, and this behavior amplifies the heating effect of other greenhouse gases too. When they warm the atmosphere, more water vapor can be stored, leading to even more warming. Most water vapor is invisible, but a minority forms the clouds that we see, which are particularly good at trapping heat, especially at higher altitudes. Some do reflect energy from the sun back into space, though. This offsets part of the warming. So, greenhouse gases from human activity are causing the planet to warm. But what would happen if we completely stopped emitting them? The challenge is that even if we did completely stop emitting them, the amount already emitted won't instantly disappear. So how quickly would the levels go back to how they were before we began our greenhouse gas emissions? The methane would dissipate in around 10 years, but it could take hundreds of years for the level of carbon dioxide in the atmosphere to do the same, and even longer for the oceans. If we want to stop the planet warming, ideally, we not only need to reduce our emissions, but find ways of mopping up the excess greenhouse gases that are already there.